This section is mostly on the solution, and the solution has two components called the solute and the solvent. Now, the boring definition is that the solvent is the component whose physical state is preserved when the solution forms. So when I said sugar solution earlier, sugar is a solid and water is a liquid. So the solvent would be the water because it's a liquid, and you still have a liquid sugar solution stuff. It looks like a liquid. The solute is the other solution component. Now, I like to think of the solute as the exciting part because when you think of a sugar solution, you think of something sweet. You don't think about the water. So the solute is the more exciting part. Hydrochloric acid is HCl in water, and the HCl is the quote-unquote exciting part, and water is the boring part. So anyway, any of these definitions you want to use are totally fine. Now, when you are taking a solute and putting it in a solvent, you have to make sure that they are soluble. And soluble just means that they dissolve. They form like one phase, if you will. If you have an insoluble piece, then it doesn't dissolve. And that's important too. So if you put like most rocks in water, they go to the bottom, all right? Those aren't dissolving. We would call the rock material insoluble in water. This is a list that's going to be very helpful in this section, and this is basically a table of when things dissolve in water and when they don't, all right? And there's lots of pieces. We're going to break this down a little bit easier, but I want to show you first of all how to tell if something is water soluble or if something is not. Now remember, soluble means that it dissolves. Insoluble means it doesn't dissolve. And if you look at this table, here on the upper left-hand side, those are all things that are water soluble. So you would write AQ next to them, which means they dissolve in water. But there are some exceptions on the right-hand side, and we'll talk about those. Further down the chart, on the lower left part, all of these guys are insoluble. So those you would put a S next to, they don't dissolve in water. Those are the rocks in water kind of material and stuff. However, just like the upper part, there are some exceptions to this as well, and the exceptions would be AQ. So again, you can think about the upper left and the lower right sections as being soluble, AQ. But the upper right and the lower left, those are when you're going to have things that are insoluble. They don't dissolve. So let's look at three examples here on the right. Let's say that you wanted to know if barium nitrate was water soluble or not. So BaNO3 question mark, like you're not sure. Usually what people will do is they'll look at the non-metal part. And in this case, that would be the nitrate ion. And nitrate, if you look at this table long enough, is right there. And nitrate is in the upper left part. It's soluble. There are no exceptions to the right of it. So BaNO3 always aqueous, soluble, all right? Let's look at the next one. Barium chloride. The question is that soluble or not? Barium chloride has a chloride, and chloride is right there. And most chlorides, bromides, and iodides are soluble except the silver, mercury, and lead 2+. So barium is not silver, mercury, or lead 2+. That means BaCl2 will be soluble. Now, if this compound would have been PbCl2, lead 2 chloride, lead is an exception. So lead 2 chloride would be insoluble, but barium is not silver, mercury, or lead, so it is soluble. And then finally, BaSO4. If you're curious if that's soluble, again, usually the nonmetal is the place to start. Sulfate is usually aqueous, usually soluble, but there are some exceptions. And if you look over there, lo and behold, barium is one of the exceptions. So what that means is that while most sulfates are water soluble, barium sulfate, barium's an exception, barium sulfate is not. So you would write it as BaSO4 solid. The first two we looked at, barium nitrate and barium chloride, those are aqueous. They are soluble, all right? But that last one, barium sulfate, it is not soluble. So you would not write write it BaSO4AQ, you would write it as BaSO4 solid. Barium sulfate does not dissolve well in water. This table is a little weird at first, but it is something that's going to be important in what we're looking at. Notice in the upper left that sodium, potassium, ammonium, as well as these ions here, especially nitrate, always water soluble, no exceptions. And that's going to be a good little grouping there to know. Also, I pointed out two other ones we're going to run into a lot. Chloride, bromide, and iodides, usually AQ unless they're silver, mercury, and lead, like we talked about. And most sulfates are aqueous, but barium sulfate is one we're going to run into a lot. So barium sulfate is insoluble. You'd write an S next to it. Also, if you look in the lower left part, most of the big negative polyatomics, for example, carbonate and phosphate and oxalate and chromate and sulfides and hydroxides, etc., most of those are insoluble, so you'd write a little S next to them. However, ammonium and the alkali metals, and alkali metals are the sodiums, potassiums, lithium, stuff like that, those would be exceptions. So you can have an insoluble carbonate with most metals with it. However, if the metal happens to be sodium, potassium, lithium, etc., or if it happens to be ammonium, then you would write AQ next to it. So with a little bit of work, this thing is pretty easy to figure out. We're going to use this in this class, Chem 221, and all the way through Chem 223. So this is a good thing to remember. Obviously, this is a little bewildering and stuff like that. So this is kind of like a cheat sheet, if you will, as to how things work. These guys right here, all right, I'm going to circle them. And those are sodium, potassium, lithium, ammonium, nitrate, chlorate, perchlorate, and acetate. Those are always AQ, all right? And there's no exceptions to that for our classes. And most of the time, sulfates, chloride, bromide, and iodide are soluble. But like we talked about earlier, barium sulfate is an exception where you'd write S next to it because it's insoluble. And chloride, bromide, and iodide are usually soluble unless they're with those almost magical silver, mercury, and lead ions, and we will run into those. So at the very least, if you can know this part, that would be cool. But again, the whole list will be important in certain places. This question says, which of the following is the only insoluble salt in water? All right. And this is a time when you can absolutely use that chart on the right if you have access to it. And again, some things to help you remember is that anytime you have sodium, potassium, lithium, nitrate, acetate, etc., those will always be AQ. And if you look at this list, nitrate is one of the ones I just mentioned. Sodium is one of the alkali metals. Potassium and lithium are all examples of ones that are always AQ. Notice that carbonate is often insoluble, but it's with an alkali metal, so it would be aqueous. Ammonium is also always AQ, so that's nice. Now, chloride, bromide, and iodide are usually AQ, and with lithium, that's definitely the case. But here's another one. Here's iodide, and look at what it's with. It's with lead, and the exceptions to chloride, bromide, and iodide are silver, mercury, and lead. So the PbI2 would be the insoluble salt in water in this list. So for all of those, A through E, you would write AQ, except C. You would put, if you will, a little S next to it. So this is one way that chemists can use to figure out the state of matter. Like, does it dissolve in water or does it not? And this can be really handy.
Potassium permanganate is an ionic compound. It dissolves readily when mixed with water. Dissolution involves the breaking of the bonds that hold the compound together. The ions become distributed throughout the water, forming a solution. Water molecules are made of hydrogen and oxygen. The hydrogen side of the molecule has a positive charge. The oxygen side is negative. When water molecules contact an ionic compound, such as potassium permanganate, their positive sides are attracted to the negative ions of the compound, and the negative sides of the H2O are attracted to the positive ions in the compound. These attractions allow the crystal lattice to break down, and the compound dissolves.
When something dissolves in water, for example, potassium permanganate, which is that cool purple solution in the lower left corner there, that there's an interesting process that happens. Now, potassium permanganate has ions, and an ion is just a charged species. So in KMnO4, you would have a K plus potassium ion. You'd also have the permanganate ion, MnO4 negative 1. But what happens in water is water has a really neat property where it's able to dissolve a lot of ionic compounds. And water has kind of a triangle kind of shape to it there, you can see. And where the O is like at the top part and the hydrogens are at the side. And in Chem 222, we're going to look a little bit closer at that. But for right now, water has a slightly positive and a slightly negative side. So what happens is the water molecules will surround the K plus and the MnO4 minus ions, and they separate them. And that's no small feat because ionic bonds are super strong, but they're able to coordinate the waters around it. One side is more positive, one side is more negative. The oxygen is the more negative side, and the side with the two hydrogens is the more positive side. So it gets around them, separates the Ks from the MnO4s, and that's really what solution is. And the picture in the upper right corner shows like a solid ionic compound, and then it shows little pieces breaking down. That's really what happens when a solution is made. So an aqueous solution, all right, when you write AQ, all right, KMnO4, AQ really is not KMnO4 anymore. It's actually K plus aqueous plus MnO4 aqueous. The positive and negative ions dissociate from each other in water. Now, most of what we're going to look at in Chem 221 through Chem 223 are aqueous water-based solutions. This does happen in other solvents as well, and you'll look at some of those in organic chemistry if you take it the second year chemistry course. But for right now, just realize water has this really cool ability to break up the cations from the anions, and most solvents don't do this as well as water. That's what's really cool. And of course, water is around us all the time, which is good for life and stuff like that. So making an aqueous solution really involves, for ionic compounds, breaking up the cations from the anions, the positive ions from the negative ions. Question you might be asking yourself is, how do you guys actually know that ions are present in solution? Well, that's a good question. And really it has to do with electrolytes. Now, electrolytes, the things sometimes purported by sports drinks to help you better and stuff like that. Electrolyte is a real thing. I'm going to leave the discussion of sports drinks for another conversation, but an electrolyte is just a solution that can conduct electricity, and it conducts electricity because you end up with a lot of positive and negative ions. And you can have strong electrolytes, which are compounds that conduct electricity really well. And the little picture on the right-hand side there, that's copper 2 chloride. And copper 2 chloride is a strong electrolyte. Strong electrolytes dissociate 100% into their ions. So in copper 2 chloride's case, that would be copper 2 plus and chloride. And then when you put electricity through the copper 2 chloride solution, which is what they're doing in that picture, the light bulb lights up, and that means that the electricity is being conducted through the ions. If you have ions running around, electrons from electricity can be transferred from like one side of the plates to the other. And we'll talk a little bit more about this in Chem 223, and physics you'll talk about it a lot more. But for our purposes right now, an electrolyte is just a solution that is able to conduct electricity through it. And if you're going to have that happen, you must have a lot of ions. So a strong electrolyte is just a compound that dissociates almost 100%. We'll assume it's 100%. That potassium permanganate example we looked at earlier, that's a strong electrolyte. It breaks up 100% into K plus and MnO4 minus. HCl, hydrochloric acid, is another great example of a strong electrolyte, and so is sodium chloride. Notice again, all of these have positives and negatives. H plus, Cl minus, that's the positive negative. K plus, MnO4 minus. Mg2 plus, Cl minus, Na plus, Cl minus, etc., etc. You have to have a lot of ions running around. Strong electrolytes are dissociated 100% into their ions.
A strong electrolyte is a compound that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
Strong electrolytes are really important in chemistry. Hydrochloric acid is a great example of a strong electrolyte. The HCl does not stay as HCl in water. It breaks up into H plus and Cl minus, and it's basically 100%. So that means you put a mole of HCl in, and you end up with a mole of H plus and a mole of Cl minus. And again, all strong electrolytes are that way. That includes the copper 2 chloride, that includes all the sodium, potassium, stuff like that. Lots of examples of this.
A weak electrolyte is a compound that only partially ionizes in solution. Some hydrogen ions dissociate from acetic acid molecules, but others may rebond at the same time.
There are lots of examples, though, of things that dissolve in water, but they don't dissociate into the ions. These are called weak electrolytes. And a weak electrolyte, maybe for every 10,000 or so molecules, one of them will break up into a positive and negative combination, but the other ones will stay the same. A real common example for us right now is acetic acid. Acetic acid has CH3CO2H, and the H on the end is actually the acidic part of the acetic acid. So when it dissociates into the ions, you end up with the acetate ion and the H plus. But the difference between acetic acid and like hydrochloric acid, which we saw earlier, is that this is much less efficient. Like I said, it's, depends on the compound, but I think acetic acid is about 1 in every 10,000 molecules. So if 10,000 molecules of acetic acid are placed in water, only one of them breaks up into acetate and H+. All the rest of them stay as the CH3CO2H. You can think about the bonds connecting them as being more resistant, if you will, to water trying to break them up. Now, weak electrolytes, if you place them in a solution and you try and throw electricity into them, the bulb is weak or it doesn't conduct electricity very well. And weak electrolytes definitely don't conduct electricity to the same extent that the strong electrolytes do. So a weak electrolyte just doesn't have the ions running around that strong electrolytes do. You'll get a much weaker light bulb signal, if you will, with a weak electrolyte. We're going to look at a lot of different weak electrolytes in future lectures. There are also solutions that don't conduct electricity at all. These are examples of compounds that do dissolve in water, but they don't dissociate. So let's make that clear right now. This compound right here is ethanol, and ethanol is essentially drinking alcohol. And ethanol, when it's placed in water, they dissolve, all right? So you only see one component. However, ethanol does not dissociate into the ions. Like you don't have a CH3CH2O negative and an H plus running around. These stay in the molecular form. There's no reason for that H plus to go off. And there's lots of examples of these kind. Sugar is a good example. Acetone, if you've used that, is another example. All of these are what they call non-electrolytes. And you try and place these in water, nothing happens. There's no electricity because you don't have any positives and negatives.
Some compounds that dissolve in water, such as ethanol, do not dissociate into ions at all. Such compounds are called non-electrolytes.
So these compounds are called non-electrolytes. They do not conduct electricity. These compounds do dissolve in water, but they don't dissociate in water. So let's look at the possibilities. You can have compounds that dissolve or don't dissolve, and that's what that table was for. So we saw, for example, barium chloride dissolves, but barium sulfate does not. So that's the first test. If they dissolve, then you can also think about if they make an electrolyte or not. And compounds with ions in them usually are strong electrolytes. So barium chloride we saw dissolved earlier, that's also a strong electrolyte. All right. If you had something like acetic acid, it dissolves, but it's a weak electrolyte. Only 1 in 10,000 or so actually break up to a positive and negative. And finally, there are some compounds like sugar and ethanol and acetone. They dissolve, but they don't dissociate into ions at all. So they don't have any electricity that works on them as they go through. All of these are going to be important things as we go through these discussions.